I'll be presenting our work on novel microwave-based non-contact edema severity monitoring using with machine learning. Let me start with the term edema. So edema is basically water accumulation in the interstitial spaces. It is not a disease by itself, but it can occur, it can happen due to several conditions. So what happens is that when there are fluid that flows through the interstitial spaces and that the accumulation increases, it increases so much so that there are swelling on the peripheral systems like your hands or legs that swell up. Now, edema can be of different types. For example, there is cerebral edema. So that is some fluid accumulation inside your brain. There can be pulmonary edema, which is fluid accumulation in your lungs, and peripheral edema. So peripheral edema is, let's say, like most of us, even without any medical condition, sometimes have experienced it. For example, if we sit or stand for a long period of time, we see there is some swelling that happens on our lower leg. So that is also edema. Now, the peripheral edema can be caused by a lot of different conditions. Heart failure can be one reason for it. There is venous insufficiency, kidney diseases, or it can be due to some effects of some drugs that some pharmaceuticals or drugs that the person is currently consuming. It is very prominent or prevalent with the woman, the pregnant woman also. Now the importance of edema monitoring. So the early you detect, so let's say, for example, we have fever. So the fever is just a symptom for some kind of disease that we might be having. So similar to the edema, so if we can detect and quantify the severity of edema, it will help us to detect the disease and then to manage it. So early detection, disease management, and obviously improving greatly on the patient outcomes. Now, how it is done till date? So the most common way of detecting edema till now is just only visual inspection. So you go to a doctor, he will just look at your lower limbs and see whether it is swollen or not. And there's this thing called pitting edema. So what they do is, so they will just put a finger and they will just press it. So how much the skin that goes inside due to the swelling, and then it comes back. There's that time that it takes to comes back. So that is called the pitting edema scale. So they categorize it, the severity depending upon that. And then there's this weight monitoring. What happens to the patients who are who has to go to dialysis. So they need to remove their body fluid. So the whole bad fluid needs to be removed and recirculated. So for them, how much amount of fluid that needs to be removed during dialysis, how do you know that? So there is no way of quantifying it. So generally it is done that, let's say a person before and after dialysis on particular day, his weight is taken, and the next day when he comes, his weight is again taken. So based on this difference of weight, they just do a rough estimation of, okay, this much amount might have been increased due to the accumulation of the fluid. So now let us remove, let's say, this much ml or liter of fluid from the body. So these are these standard methods that are being followed till date. So now what is the need of unobtrusive edema quantification? So first of all, we need to quantify edema. Just by saying that, okay, there has been water accumulation is not enough. And another point that I would like to mention is that for any sort of visible or the measurement type of assessment, that comes only when the water accumulation has been to such an extent that it is you can visually see it. So what if you can detect the edema before that? So the water has, let's say the fluid has started accumulating, but it is not it is not visibly clear, but then also if we can detect it, that would have been a game changer for the medical practitioners. So we are proposing microwave as a technique for non-invasive quantitative, and which also obviously have this capacity of remote monitoring, which will lead to personalized and treatment effectiveness and obviously improved outcomes. So our proposition is that we want first of all, a non-contact, non-invasive method of edema detection. So what we have done in this particular work is we are proposing edema detection and severity monitoring unobtrusively through microwave, and which is driven through machine learning approach. So here we have, like, based on the percentage of water accumulation, the edema we have like categorized the edema into like low, medium, and high percentages of water accumulation. So what we initially did is that generally, so the antennas, so we have a design of a like microstrip patch antenna. The standard patch antennas, these are designed on free space. Like, so what we have done is that we have designed the antenna where like simulating it by dielectric loading in front of a human phantom. So numerical human phantom we have kept at a 10 millimeter distance, and we have like designed and fabricated the antenna that way, so that whenever there is even a small change in the dielectric properties of the human tissue due to water accumulation, the loading of the antenna will be changed effectively, and that can be like seen in the reflection characteristics. So for this, we have taken a very crude method. So initially, so you need either human tissues or some sort of human phantom. So what we have done here is we have taken like polyurethane foam. So these are very, so in general terms, these are called some floral foam. So this has a capacity of holding the high extent of water. These are highly porous and inhomogeneous. Thus, this can emulate human tissues or tissue properties. So we have cut it open, and what we have done is we have made a hole in this. If you see the picture here, so we have made a hole in this, and we have like water-filled balloons of different quantities. So we have like with these water-filled balloons, we have varied the water percentage from let's say 1% to 44%. So we have filled these water-filled balloons and put it inside the hole that we have dug in, and then this is the cover with the PU foam that we have again put it on. So we have this patch antenna which we have put over the PU foam with a distance of obviously 10 millimeters, so it is not touching, so it is at a non-contact. And then, so we did 3 different types of ways in which we have emulated edema. In one way, we have filled the water balloons and put it at the bottom. Secondly, so when we put it at the bottom, that means, so you see the bottom of the balloon is fixed. So whenever we are increasing the water content, what is increasing here so it is increasing in the top way. So that means the distance of the antenna from the top surface of the water, that is changing with the increasing amount of water. Here we have a water-filled balloon at the top. That means the distance of the water level with the antenna is always fixed. What is increasing when we are increasing the volume, water volume, then it is this is increasing downwards direction. And the last one that we did is we have put another part of a PU foam, and we are injecting it with water. So when we are injecting it with water, then we are not sure that where or in which direction the water is being spreading. And that is very similar to how in the interstitial spaces, the water actually goes in different directions, and there is no particular science, like there is no particular way that you can say that it will go downwards or sideways. So these are the reflection data that shows with a change in the water volume percentage. So when I say healthy, that means there is no water accumulated. So just to mention a point here, so we took this PU foam as a human phantom, and we were like introducing water little by little and seeing the variation in the reflection. So one of the like aim with this is there is only one characteristic that is changing, that is the water volume, and we are seeing whatever the change in the reflection characteristics are there, that is only because of the change in the water and no other possibilities. So let's say if we have started with the human tissues or like ex vivo animal tissues, then there would have been a lot of different characteristics that we don't want to see in the first instance. So what you see here that with respect to the healthy, that means there is zero water present. there's a difference or there's a variation of the reflection parameter with the water. There are differences, but just by looking at these reflection characteristics, you cannot say that which reflection like corresponds to which volume of water accumulation. So that led us to extracting some electromagnetic features. So we extracted basically three features. One is fractional bandwidth, another is the like change in the resonance frequency, and the third is the change in the percentage change in the like reflection magnitude. So this actually worked, or this was taken as the feature vector. So when we plotted these three features for the three different experiments that we did, so the columns actually represent the three different experiments that we did, and the rows that represent the three different features that we have. So if you see that for the experimental 1 and experiment 2, for both the antenna tuned in free space and the antenna dielectrically tuned, the trend is more or less same. But when for the experiment 2, that is going in exactly opposite direction. Also, we see that the water, when the water is less than 5%, that has more uncertainty in the like patterns, and that has a linear pattern when it goes beyond 5%. So what we did is that, so here it shows the whole, so we use the VNA, which is attached to our antenna. We took the reflection data, and then when we measured the reflection data, extracted these features, and that acted as a feature vector which with which we trained our classifier. And finally, when a new set of data with a certain volume of water came, then we were able to classify it based upon different edema severity, that is low, high, and medium categories. So what we found with the different combinations of features and the classifiers is that, if you see in this confusion matrix, so there is a error at the low edema percentage. So as I mentioned earlier also, like when the water accumulation is less than 5%, the uncertainty in the data or the features is much more. So that actually is quite expected to be like errors in the low edema severity detection. And another thing to be also like noticed is that none of the features alone were competent enough to do the severity detection. So when we detect, when we took a combination of all the three features, and when it was done using the dielectrically tuned or loaded antenna, then it works. So, and we have shown that it is actually better than like whatever is like available till date. So just on the concluding remarks that we have presented a ML-based non-intrusive edema monitoring and severity detection. Thank you.